Okay, now I need the cursor to. Okay, got it. Sorry. Got it.
All right, so hi everyone. Welcome to the second gravity seminar. And today our speaker will be Horng Sheng Chia from the Institute for Advanced Study in Princeton. Horng Sheng completed his PhD in Amsterdam under Daniel Baumann and then moved to the Institute. And we're happy to hear from him about In Pursuit of Love, Black Holes and Gravitational Waves as Multifaceted Probes of the Universe. Please take it away.
Yeah, thank you, Shahar. Thank you for the introduction, and thank you all for having me, and I hope that all is well back at home. So today I want to talk about several research topics that I've worked on, and they all seem kind of naively separate topics on black holes and gravitational waves, and in fact some aspects of dark matter physics. But I hope we've become clear at the end of the talk that one can sort of nicely connect the few different subfields and do some cool research as well. To start with, I think this is sort of by now a customary slide, just showing that, highlighting that we really are living in the golden era of gravitational wave astronomy. I mean, by now the LIGO-Virgo Cagra network is running 04. You can see on the bottom right panel, 04 is the fourth observing run. But before that, from 01 to 03, we've detected order around around 100 events also, so which includes binary black holes and binary neutron stars and a few black hole neutron star binaries. But the projected number of detected binaries is expected to increase very rapidly by the end of the decade, and certainly by the next decade. As you can see, unfortunately, I don't have the cursor with me, but as you can see on the bottom right picture, where 04 and 05, or even up until Voyager, which is supposed to be this updated LIGO detectors, we're expected to see at least an order of magnitude increase in the number of detected binaries. This is definitely true in the next generation detectors for CE, which stands for Cosmic Explorer, or ET, Einstein Telescope, which are in completely new ground-based gravitational wave detectors, where again, the rate estimates have large errors, but the expectation is that we're going to go up to like 10 to the 5, 10 to the 6 or so number of detected binaries. And this plot excludes LISA, which is a completely different frequency band. It will look at completely different mass ranges of binary black holes. Okay, so the future of the field is absolutely bright. So given the large influx of data that we're seeing, one of my key research questions is to try to ask, what can we learn about physics and astrophysics given the large volumes of data that we're about to see? So in the rest of my talk, I'll be focusing mostly on binary systems, because binary black holes are by far the loudest and the most abundant sources of gravitational wave. And so, a lot of my research involves what can we learn from, future detections of binary systems. So as you can see from this figure, in addition to the usual source parameters, which are the mass and the spin of the binary components, it turns out that when the binary shrinks and as it approaches merger, various sort of what we call finite size effects can start to become important. And I explain what these coefficients K and nu are, but these are basically the various other macroscopic quantities that describe, how each of these bodies would react to the perturbation that's being sourced by its binary companion. And these observables are important because they will actually affect waveforms, especially the phase of waveforms, which is what we're most sensitive to in gravity wave astronomy. And one class of finite-sized effects are commonly referred to as tidal effects. Tidal effects refer to this effect where, how would a body react or respond to the gravitational perturbation that's being sourced by its external tidal field. And until recently, there has been sort of some confusion and some open problems as to what are the tidal effects of black holes. And in the first part of this talk, I will, I'll share some results and some insights into recent understandings of the tidal effects of black holes. Specifically, if you look on the left of this panel, you would see that there are two types of tidal effects: tidal deformation, which corresponds to the conservative effect, conservative tidal effect, which arises due to the deformation of a body when it is perturbed by external tidal field. And these, the tidal deformability of a body are quantified by a set of parameters that's commonly referred to as Luft numbers in the literature. And in the first part of my talk, I'll briefly describe, recent understandings that how the Luft numbers of Kerr black holes vanish. So, black holes have 0 Luft numbers, at least in the static limit, which is a little caveat that I'll come back to. On the right-hand side, these correspond to the dissipative response of a Kerr black hole. And tidal dissipation of Kerr black holes has been relatively understood for a few decades at least. And here it is understood that, in addition to the usual intuition that one can permanently lose energy and angular momentum into the black hole event horizon, which is kind of what you would naively think, what the black hole, the one-way membrane, the one-way nature of the event horizon does. There's also the opposite effect, which is the fact that when you have a highly spinning black hole, one can spontaneously extract energy and angular momentum from a highly spinning black hole. And this goes on, and this is a process that's known as black hole superradiance in the literature. So why is understanding the black hole tidal effects, both the Luft numbers and the dissipation effect, useful in physics and in astronomy? Well, for starters, knowing that black holes have vanishing Luft numbers is critical in order for us to distinguish the nature of sources when we detect gravitational waves. So here you would see that on the top left, you would see an equation where delta Q is the induced change of the quadrupole moment of a body. On the right, you see E, which is the external tidal field. And lambda is this overall constant of proportionality, which has 2 pieces to it, which I show on the right side of the equation. And you see that lambda has 2 parts to it. One is this order 1 coefficient that we call K2. I'll explain what it is, but K2, one can interpret it as another dimensionless Luft number. But crucially, what we measure best is lambda, and lambda scales very sensitively to the radius, which is r, divided by m, which is the mass of the body. And r over m is sometimes also known as the compactness of a body. So the key point here is that for black holes, K2 is 0, so that, the Luft numbers of black holes are 0, so one wouldn't be able to measure these effects for binary black holes. But for anything other than black holes, say a neutron star, K2 is non-vanishing, but most importantly, it scales with the radius of the body to the 5th power, which is a very sensitive dependence on its size. And this is in fact how, for example, in GW170817, which is the first binary neutron star that we have detected, by measuring, or rather I should say, by constraining lambda for 2 of the neutron stars, they've been able to place some constraints on the mass radius relation and the nuclear equation of state of neutron stars, as you can see on the bottom left panel, where lambda 1, lambda 2 corresponds to the individual Luft numbers of the 2 neutron stars. It's also interesting that, you see that GW170817 consists of neutron stars of the mass of about 1.5 solar mass for each of these neutron stars. But it's well known that if you have sub-solar mass neutron stars, if the masses of neutron stars are smaller, lambda can be much larger than 1,000 or a few hundred that's been constrained by GW170817. So you see that on the right side, on the right panel, where what's being plotted are a few nuclear equation of states. It's been understood for some time that when you have sub-solar mass neutron stars, as the mass decreases, lambda can go all the way up to, I don't know, like 10 to the 4, 10 to the 5, or easily 10 to the 7 or so, because of this very sensitive dependence on the radius. Okay, so some people ask me, like, isn't this like by naturalist arguments? You didn't expect Luft numbers to always to be order 1 and so, and that is true for K2, but that's not true for lambda, which is what we measure best in gravity wave astronomy. And so one can very naturally have these extremely large values of Luft numbers that will have a very important imprint in especially in the phases of gravitational waves.
But can't you just prove that you cannot have black hole neutron stars with mass significantly smaller than 1?
Do you say, are you asking about black holes or neutron stars?
No, neutron stars. I mean, neutron stars One can demonstrate the neutron stars less than about one solar mass simply cannot form.
Yes, that is exactly. So I think that is the expectation in the astrophysics literature. My understanding, speaking to folks who work on the neutron star topic, have told me that they've not seen the formation of such subsolar mass neutron stars in simulations. It'd be interesting if there's one.
It's nothing to do with simulations. The potential barrier that you have to pass in order to produce a low mass neutron star is sufficiently large that you can, without any simulation, analytically, you can demonstrate that such objects cannot exist.
Regardless of the equation of state?
I
think people have told me with some...
I think it is regardless of the equation of state, because of course it depends. The size of the barrier depends on the equation of state, but because of the fact that these objects are rather large, they are not so dense. So the equation of state in this regime is one that is fairly well. It's better understood. So there is not much freedom there.
Yeah, that is my understanding as well, indeed. And yeah, and I'll show later that we did a search. Spoiler that we did a search for objects with large left numbers, but unfortunately we had to, for technical reasons that I explained, it's hard to target the low mass regimes. I mean, we're hoping to look for realistic realistic neutron star masses above one solar mass, let's say, but with large left numbers, because that would be sort of probing different types of nuclear equation of state, for example, but that is computationally expensive to do. On the theory side, I mean, again, I'm no expert by any means in this topic, but indeed, you know, what you say is consistent with what other folks tell me as well. One can ask what happens with white dwarf. So we never really observe two white dwarfs, like an orbiting white dwarf in the LIGO-Virgo band, because they're too big and they cannot merge within the LIGO-Virgo band. But we can ask with LISA or with some kind of decihertz detector, if we have sufficiently close binary white dwarfs. One can ask, you know, then the radius obviously matters in that case, right? Okay. So that was for like astrophysics, but I'm sure many of you have heard of many proposals for what other types of beyond standard model compact objects that could exist in the literature. I'm not going to go through any detail here, except just to say that in virtually all of these cases, lambda is unbounded because there are always model parameters that one can tune or one can choose, which leads to sort of large sizes of these bodies. And so their lambda is it can virtually be unbounded. So, you know, knowing that black holes have vanishing left numbers is important because it will allow us to distinguish the nature of these different binary components when we observe the gravitational wave signature. On the other hand, for the black hole dissipation, this is interesting in many reasons. In astrophysics, and I'm going to go into detail, in astrophysics, it's well understood that there's a phenomenon that's known as the Blanford-Chinayak process, which is responsible for the emergence of highly energetic jets around the center of Milky Way when you have a supermassive black hole that's surrounded by accretion matter. But in the focus of this talk will be on beyond standard model physics, where it turns out that black hole superradiance is a very interesting probe of a class of dark matter candidate that's often referred to as ultralight dark matter, wave dark matter, ultralight bosons. There's several names for it. And what happens is that you would see on the left where what happens is that when the Compton wavelength of the boson field is comparable to the size of a rotating black hole, this field can spontaneously extract energy and angular momentum from the black hole through the superradiance phenomenon that I described earlier, such that the black hole will spin down and you will form a cloud of bosonic condensate around the black hole. And it's remarkable that the structure of this system, of this boson condensate, is very analogous to the proton-electron structure of the hydrogen atom. And therefore, these systems are often known as the gravitational atom. And this is, in fact, not just a qualitative analogy. There's a precise mathematical analogy between the two, which I'll describe in the second part of this talk. The intuition, of course, is that In the case of the hydrogen atom, you have a proton at the center and a wave function of electron around the proton, and they're bound to each other through a 1/r Coulomb electrostatic potential. Right now, instead, you have a black hole at the center and a cloud of boson condensate around the black hole. And in leading order, they're bound to each other through a 1/r Newtonian potential. And I'll make this analogy more precise later on. So just to, let me see if now the cursor, you can see my cursor now, can you? Awesome, I don't know why it appears now. So just to convince folks who have perhaps not heard of this story, that this is not really a crazy idea. This is a numerical relativity simulation, which starts off with a highly spinning black hole and a random field configuration of a vector field specifically, but that's a technical detail. This is the first full dynamical, pure numerical relativity simulation of the formation of these gravitational atoms that can be formed around a highly spinning black hole. And there's no new physics involved here, in the sense that all you need is really just vanilla GR. There's no modified gravity involved. Plus, all you need to have is a minimally coupled massive boson field. It can be a scalar or a vector. You do not need to have sort of nonlinear self-interactions in the matter sector, like an axion. In fact, having an axion term would pollute, or would rather complicate the story. So this is a very nice probe of BSM physics.
A question. So could you explain these fluctuations that we see close to the horizon? Is this?
I think it's a gauge thing. I think it's a gauge thing.
Okay.
I mean, as you know, in numerical relativity simulations, everything is gauge dependent, and you have to choose some coordinates.
Okay.
That's part of the reason. I haven't asked Will or Franz about this. I was curious when I saw that as well. I extracted this directly from Will's website. The other thing I would say is that it turns out these clouds are actually rotating. So they don't just grow as like a stationary configuration. Well, they're stationary, but they're actually oscillating as well. So I suspect part of that fluctuations that you see at the center arises due to that. But yeah, gauges is always an issue.
I see. Okay, thank you.
In simulations, yeah. Yeah, I was curious about the same question as well. So a lot of my PhD was in fact trying to understand what the dynamics of these gravitational atoms when they're in binary systems. I won't go into any detail because I definitely won't have time. But it turns out that there are certain critical frequencies that's dependent on the mass of the boson and the intrinsic spin of the boson, where when the orbital frequency matches with these resonant frequencies, there's a non-perturbative effect. There's a non-perturbative dynamics that can backreact on the orbit, and out comes a waveform that looks very different from those of a classic vanilla binary black hole in spiral. Again, definitely won't have time to talk about this. I have some slides, supplementary slides, if anyone's interested. But instead, the focus of this talk will be on the top left of this slide. See, my cursor is gone now, annoying. Where I'll be talking instead about the effect of the fact that the cloud is big. It can have a very non-negligible effect, tidal effect, on the phases of gravitational waveforms. And I'll talk about that as an example of doing a broad search for compact objects that are not just black holes and neutron stars, but instead having these Luft numbers as a parameterization of new physics. Let these Luft numbers be big in the waveform and conduct a brand new search in the public LIGO and Virgo data to see whether we have missed such speculative but also potentially interesting type of binary component in gravitational wave astronomy. So the upshot is that in a recent work, we completed a full search on the 01, 02, 03A, 03B public LIGO-Virgo data, seeking to search for binary systems where at least one of the components of the binary has these large Luft numbers. The upshot, no surprise, is that we did not detect any new signatures. But I also tried to use this search as a concrete example of a broader strategy, which is to be able to detect other types of new physics that relaxes the usual assumption that are quasi-circular binary black holes, which has been sort of dominated. This is the strategy that's been dominated by whether by the LIGO-Virgo collaboration or other external folks in the external collaboration. So use this as an example to motivate that strategy a little bit. What's interesting that I should highlight is that even though we did not detect new signatures or new physics in this work, we were able to recover many of the known binary black holes that has been recovered in previous works. So this is to demonstrate that our pipeline, the method works. It's just that there's no new physics in the data as of now. So my understanding is that the audience has a broad interest and diverse backgrounds. So I hope that's kind of clear. And I'll split the rest of my talk into 3 subparts, each of them relatively brief, but just to give you a sense, that one can do black hole physics, dark matter physics, and gravitational data analysis in a sort of nice cohesive fashion. Any questions before I move on to the to these few parts? Okay, if not, in order to understand tidal effects in GR, it's useful to take a step back and instead understand how tidal effects are formulated in Newtonian gravity. And in this case, at least in a static limit where the external perturbation has no time dependence, a body will respond to the static external tidal field by acquiring an induced mass moment. So delta Q is the induced moment expanded in multiple expansions. On the right-hand side, you have E, which is the external tidal field, again, expanded to all orders in the multiple expansion of the tidal field. R is the radius of a body, and it scales with some power, which you can infer directly from dimension analysis. And K now are the so-called Love numbers in the literature. I used to show K2, where 2 labels L equals to 2, so it's the quadrupolar Love number. But in principle, one can define Love numbers, for all moments in the multiple expansion as well. Okay. Now, of course, in practice, the perturber is not static, but instead is varying with time, and so the tidal response is dynamical. And in this case, the induced moment, if you see in the first line of the equation, the induced moment is given by the convolution of the external tidal field E with the response function, the total response function that I call F in the first line of the equation. In the limit where the external tidal field is slowly varying with time, one can perform a systematic expansion in time derivatives, and one obtains the second line of the equation instead, where at leading order, you will recover the static tidal terms that showed the slide early on. But right now, there are new corrections to the tidal response, which is proportional to E dot, the time derivative acting on the external tidal field. And this operator is, it corresponds to tidal dissipation. The easiest way to see that this is a dissipative term is the fact that this involves a single power and time derivative. So it is not invariant under time reversal, and so it does not conserve energy, and thence its dissipation. The coefficient nu are the so-called dissipation numbers or viscosity of the body, and tau naught is a typical delay timescale associated to this effect. And it is well known in the astrophysics literature that the viscosity-induced time lag introduces a phase difference. Unfortunately, I don't have my pointer, but you would see that in the picture, you see that there's a phase difference between the direction of the bulge and the direction to the orbital companion. And this effect, which you observe in the Earth-Moon system, for example, arises due to this dissipative phenomenon. So this is the relation in the time domain, and obviously convolution in the time domain corresponds to product in the frequency domain. And if one performs a Fourier transformation, you will obtain the simpler relationship given by the first line, where omega is the frequency of the external tidal field. And now the total response function F in Fourier domain is given by the second line there. And the key takeaway from this slide really is that in order to distinguish the conservative piece versus the dissipative piece in the response function, one would read off the real part versus the imaginary part of the total response function. This is sort of the key slide in a sense, but if you understand this, the fact that real corresponds to the conservative and imaginary terms correspond to the dissipative effect, you can sort of trivially understand the tidal response of black holes in GR. I won't go into any technical detail given the breadth of topics that I'll cover in this talk, but the upshot is that there has been relatively recent works, like a few years ago, where we computed the tidal response of of black holes using the Tucholsky equation. Again, won't go into any detail except just to show that in the Schwarzschild limit, where people understand what the tidal effects are, one can reproduce known results using the Tucholsky equation. And you would see the result, the second line here, F for Schwarzschild black hole has the following result, where you see that at leading order, the real part vanishes. And so the Luft numbers of Schwarzschild black holes are 0. And this result has actually been understood and has been known for quite some time in the gravitational wave literature. On the other hand, you would see that the leading order imaginary terms has the following form, where the nice thing now with the Tucholsky equation is that you can solve for the dissipation numbers or the viscosity numbers to all orders in L in the multiple expansion of the external tidal field. One can repeat the exercise and solve the tidal response for a Kerr black hole, and the upshot is that this is the result, where you see that the leading or the real part of the total Kerr response function is 0, and so the Luft numbers of Kerr black holes are 0 as well. And it's remarkable that this result is true for all values of black hole spin. It is true for both the so-called electric and magnetic type perturbations in GR, and it is true to all orders in the multiple expansion of the external tidal field. On the other hand, you see that the leading order imaginary term is a bit more complicated, but the most important term is the one shown in parentheses, is m omega minus m capital omega minus little omega term, which corresponds to the superradiance phenomenon that I briefly described earlier. In the limit where omega h, which is the angular frequency of the black hole, is 0, the term in the parentheses would have a sign such that one would lose energy and angular momentum into the black hole horizon. But in the opposite limit, where the angular velocity of the black hole is high, when spin is high, and when m is positive, the term in the parentheses can flip its sign to be positive. And in that case, one would spontaneously extract energy and angular momentum from a highly spinning black hole. And this is exactly the phenomenon of superradiance. And I'll describe how this effect can be used to probe or grow the gravitational atom. So here is a plot showing that there has been recent efforts trying to constrain both the Luft numbers and the dissipation numbers of binary black holes. On the left, you would see a plot, a posterior distribution of the Luft numbers of binary black holes, where lambda tilde on the x-axis is a mass-weighted Luft numbers that's best measured in the data. As you can see, the constraints right now are relatively poor. All the data tells us is that these Luft numbers cannot be larger than 1,000 or so, but beyond that, it doesn't give us much more constraining power with current data. But hopefully, and this is ongoing work, we should do some future forecasts where we estimate, future detectors. What are the precisions at which future detectors will be able to constrain or measure black hole Luft numbers. And similarly, on the right panel, H0 is a effective dissipation number of binary black holes that we recently derived. And the constraints here are a little bit better because dissipation appears at a lower post-Newtonian order in waveform. So we're more sensitive to dissipation numbers, but again, we're far from its theoretical value still, which is close to 0.1. But just to impress upon you that there are recent works on the data analysis frontier that try to constrain, or some people like to call it test GR. In my view, I love GR. I 100% I'm for GR, but to me, this is more like testing the nature of the binary components, whether any of them can be something more exotic that arises in BSM physics. Okay, I hope that was clear. Any questions before I move on to the formation of these gravitational atoms through superradiance? Okay, if not,
I have a quick question about the last slide. So how would your constraints on these parameters scale with the number of observed gravitational wave signals?
Good. So here we're plotting the posterior distributions of individual events. In the paper that's coming up, we also show what the constraints would look like when you stack all of these events. Say you assume that they're all binary black holes, right? And roughly speaking, if they all have equal SNR, you know, the constraint, the sigma, the standard error with scale is 1 over square root of n. And so one would obtain better constraints. What I'm showing here is more conservative in that I've not stacked. In fact, I'm just showing the constraints for individual events, and therefore they're broader. But again, as you increase the number of detected binaries by a factor of 100, you reduce the error bars again approximately by a factor of 10. And this is really where the expectation with third generation, like Einstein telescope, for example, is that we really will be able to pinpoint to very, very high precision these left numbers and dissipation numbers of black holes. Yeah, that's a great question. Okay, if no other questions. So gravitational atoms, so I just want to explain the physics underlying this numerical relativity simulation that I showed earlier. I won't play it in full. So to understand the physics of the gravitational atom, let's consider the minimally coupled Klein-Gordon equation and Proctor equation, where again, crucially, the only interaction here involved is the mass of the boson mu and the metric that's contained in the Dahlan version here, which is the Kerr metric, and there's no other form of interactions necessary. For future slides, it's useful to show what the Kerr metric looks like, at least in the large distance limit, where you see that at large distances, the Kerr metric in the so-called Boyer-Lingowitz coordinates has the following form, where m over r is the usual Schwarzschild potential of the Kerr black hole. But now there are also the terms in blue, which are the off-diagonal terms, which depend on the spin of the black hole, the term A there. And as you see, the spin of the black hole will act like a magnetic field on these on the scalar and vector fields. So when you plot the so-called radio effective potential of the Klein-Gordon Proctor equations, you would have the following. You see a curve that's being shown in this diagram, where moving to the left, we're approaching the event horizon in the so-called tortoise coordinates, but moving to the right, one just approaches asymptotic infinity. The peak of this potential is the centrifugal barrier that arises due to the fact the scalar field or the vector field contains angular momentum. But the key point in the context of the gravitational atom is the fact that now that when you have a boson mass mu at large distances, the potential would not die off to 0, but instead it will level off to a DC. It will level off to a constant value, and the height of that constant is exactly given by the mass of the boson field. And this is critical because what this means is that now with the formation of the centrifugal barrier and with the mass barrier at large distances, you would have something like a potential well that's being formed at the characteristic distance that we call the Bohr radius of the gravitational atom, where one can form bound states of such bosonic configurations when the frequency omega is smaller than the mass of the boson field. So in order to understand the direct analogy between the gravitation and the hydrogen atoms, it is useful to define what we call the non-relativistic fields, which are denoted by little psi and psi I in the first line of the equation. Well, effectively, with this definition, what we're saying is that we're peeling off fast oscillatory behavior, this e to the minus I mu t terms. We're peeling off these fast oscillatory behaviors such that the non-relativistic fields vary at timescales that's slower than 1 over mu, which is the characteristic, oscillation timescale of the boson. If one plugs in these ansatz into the Klein-Gordon Proctor equations, you obtain Schrödinger-like equations as being shown in the second line on the slide. You would see that it really is directly analogous to the Schrödinger equation that we all learned in our 101 quantum mechanics course, where the Hamiltonian, quote unquote, has this kinetic term given by the Laplacian, and now there's also the 1 over r Coulomb-like potential, where now alpha is often called the gravitational fine structure constant, and it is given by the ratio of the Schwarzschild radius of the black hole divided by the Compton wavelength of the boson field. So this alpha sets the scale. Basically, it sets almost every property of these gravitational atoms. And if you plug in typical values into alpha, you'll find that for 3 solar mass black hole, let's say, you'll be probing mu's, ultralight bosons, of the scale of about 10 to the minus 12 or 10 to the minus 11 EVs or so. As I'll explain later, in order to grow these clouds, alpha has to be smaller than order 1. And so for a given black hole mass, one can actually probe roughly 2 orders of magnitude in boson mass. I should probably emphasize that, in the context of say fuzzy dark matter, people often talk about bosons mu of the order of 10 to the minus 20 EV or 10 to the minus 21 EV. So really, really long wavelength modes, because those observations rely on typically cosmology or galactic physics. But here, the fact that black holes are smaller means that you can probe sort of an intermediate regime where the bosons are heavier than the typical context of fuzzy dark matter, but still, very, very light, dark matter candidates. So given that, the gravitational atoms obey effectively the same equations as the hydrogen atom, it wouldn't surprise you that they obey the same solutions as well. Where right now there are these so-called typical the hydrogenic radial functions, capital R here, and the solutions are labeled by a set of quantum numbers, N, L, J, and M, and it's the principal number that tells you the overtone number of the field configuration. There's L, which is the orbital angular momentum number, J, the total angular momentum number, and M, the azimuthal angular momentum number. The only difference between the scalar and vector is really that for scalar, there's no intrinsic spin. And so J and L are the same. But for a massive vector field, because they're 3 independent polarizations, J and L, they differ by 0 or by plus minus 1. Okay. But otherwise, the physics between the two are virtually identical. Again, pushing the analogy with the hydrogen atom a bit further, if you solve for the spectrum of the gravitational atom, you'll find that it looks very similar to the case of the hydrogen atom. So you see that in the equation there, the alpha squared divided by n squared term, these are exactly like the Bohr energy levels of the hydrogen atom, as is being shown on the vertical axis, on the vertical direction of the figure. So this Bohr energy levels arises due to the 1/r potential, but one can compute relativistic corrections to the Kerr metric by including 1/r squared, 1/r cubed terms, and compute higher order corrections in the energy spectrum. And in order alpha to the 4, it turns out the L dependence, the orbital angular momentum number dependence, start to appear, and these are like the fine structure splittings of the hydrogen atom, as is being shown on the horizontal axis of this figure. What's more, if you go to 1 order in alpha higher, the M, the azimuthal angular momentum number dependence, start to appear, and these terms depend on the black hole spin on A. So what this means is that the spin of the black hole will split the degeneracy between states of different values of M, and therefore, black hole spins act like a magnetic field, and these are analogous to the hyperfine splittings of the hydrogen atom. So, given, there are close similarities between the hydrogen and the gravitational atoms, but there are also crucial differences between the two. The most important difference is the fact that in the hydrogen atom, you have a regular boundary condition at the location of the proton. And so all of the states in the spectrum are stationary states. But right now in the gravitational atom, you have an event horizon at the center of the black hole. And so these states are not stationary, but they're only quasi-stationary. So what this means is that the frequency spectrum contains an imaginary term, and one can compute the imaginary terms that we often call the instability rates in the literature. And this instability rate, this gamma term, is exactly proportional to the superradiance factor that I described earlier on. And so if you have a highly spinning black hole and with positive values of M, gamma is positive, and so one can form this spontaneously form these gravitational atoms through this superradiant instability. And you can see that, again, unfortunately, can't see my cursor, but for a given value of n and L, let's say n equals to 2 and L equals to 1, you can see that the top state, the 2, 1, 1 state, the state with m equals to 1 will be a growing state in the spectrum. Not only that, it turns out that this 2, 1, 1 state has the largest instability rate. This is the term, this is the state that grows the fastest amongst the infinite hierarchy of growing states that I have in the spectrum. And so the dominant scalar configuration is analogous to the 2p orbitals. It's like the 2p state of the hydrogen atom. In the vector case, it is very similar, except that now because I have 3 independent polarizations, there are many, many more states in the spectrum. But other than that, qualitatively, it is very similar to the scalar case. The key difference here, however, is that right now, the dominant state is the state where J equals to what? L equals to 0, J equals to 1, and M equals to 1. And this is given by the state that I label in the bottom left here. And the ground state of the vector cloud, the dominant state is 1s, is because it's n equals to 1 and L equals to 0. And these are sort of directly analogous to the 1s states of the hydrogen atom. I won't go into any details here, just to impress upon you that in addition to computing the spectra analytically, we also compute it numerically. So in the bottom panels of these two plots, you see on the y-axis, what is shown is the ratio, which is the ratio of the numerics with the analytics. And you see that in the small alpha regime, the ratio goes to 1 between the two. And so the analytics work well. But at large alpha, the analytics start to, but the perturbation, the perturbative expansion of the spectra starts to become nonlinear. And so the deviation between numerics and analytics start to deviate from 1. And this is all sort of like well understood. Here's a plot showing the instability rate. Again, I won't go into details, just to impress upon you that we solve these things numerically as well, where the data points correspond to numeric data points, and the solid line is the analytic prediction. And we agree, we understand both numerics and the analytics of these systems. The final slide on this second part is to discuss that, now that we have, in my view, a very clean and very well motivated beyond the standard model proposal, one can ask how can one seek for these signatures in gravitational wave astronomy? And so obviously related to the left number story that I discussed earlier, the fact that these bosonic condensates have large size, and also I should also mention that they have non-negligible mass. So in the most optimistic case, one can extract about 10% of the mass of the initial black hole. So you start with a 30 solar mass black hole, there will be roughly, let's say, 10% of that or 5% of the mass contained in the cloud. And so this can have a non-negligible change in the quadrupolar structure of these from a black hole quadrupolar structure. And analogously, they will have very, very large left numbers. And you see that on the top right equation, plugging typical values of alpha, lambda can easily be 10 to the 9. I mean, look at how sensitive the dependence it is on alpha, right? I mean, if I reduce alpha by a little bit, lambda can be 10 to the 10 very quickly. Just to motivate that, having large left numbers is not sort of a crazy thing to have. And so, given this gravitational atom as an example of a beyond the standard model compact object, and given there are many other proposals, let's say boson stars in the literature, one can ask, how can we seek or detect these things in the data? Any questions before I move on to the last part? Okay.
Yes, I have 2 questions. Questions. The first question is just a connection with history. There was a lot of talk in the 70s about superradiance of black holes in the context of you send a wave from infinity towards a black hole, and if the black hole is rotating, then the wave can be amplified under certain conditions. How is this, what you call superradiance here, related to this all the ideas. At least it has the same name.
It's totally the same thing. Really, the only difference is the fact that now mu. So when you think of this as a scattering process, the frequency of the field omega is larger than mu, larger than the mass of a boson. And so this is the case where in a scattering event, you would just shoot a wave in with a certain frequency and extract some energy and angular momentum from a black hole, but that wave would radiate to infinity, right? But this is in the...
Here the wave is trapped because, and here you're talking about trapped wave because omega is less than. Okay, so this was one question. And the second question is, you began the introduction of this section by expanding the Kerr metric and talking just about the asymptotic form of the Kerr metric. Now, why do you need this? I mean, what will happen if you use did you use it in the whole analysis, or will things change if you use the full Kerr metric?
No. So in fact, in order to compute the spectrum here, in order to compute all of these details, I need to have the near region as well. I was just showing this equation to sort of simplify a little bit on just showing what the spin and the mass, how these terms appear in the most simplistic terms. But no, to compute, especially to compute the instability rate, where you have to carefully take the boundary condition of the black hole event horizon into account, one would have to work with the full Kerr metric, including R towards R plus, the event horizon. And so, no, this is just for illustration purposes. In practice, in actual calculation, we take everything into account.
Okay, thank you. That's what I get.
Yeah.
This is what I guessed, but
yeah, thanks.
Sure.
No, thanks for clarifying. I mean, to add on to that a little bit, in practice, you cannot work directly with the full Kerr metric because you would get these Horng equations, which are very hard to work with. In practice, what you would do is that you would expand the Kerr metric by limiting yourself to the far region, which is given by this line element, and you would expand it in the near region, and then solve the solutions independently in these regions and perform match asymptotic expansion and match those solutions. And that is exactly what we did to obtain all of these results in all of these numeric analytic results. Yeah, thanks for the question. Okay, in my final 10 minutes or so, I will try to speed up.
Can I also ask something?
Yep, sorry, of course.
Since you are dealing with the Klein-Gordon equation, which could describe a quantum particle, a quantum relativistic particle, could you go back to the barrier? Yes. Could the field actually tunnel through the barrier?
It could. Well, so first of all, just to be clear, all I talk about here is pure classical, right? In the sense that you have some underlying field of this sort, but through large occupation densities, these fields become inherently classical at large scales. Can they tunnel? I would say that when you solve for the solution, the tunneling appears in the sense that in this limit where omega is smaller than mu, the solution it decays exponentially. So it scales as e to the minus square root mu square minus omega square at large distances. And this is exactly the difference between pure plane wave and the exponential, and the exponential tail. The exponential tail is basically a tunneling phenomenon, right? So this is exactly incorporated. I don't have an equation here, but this is captured in the hydrogenic radial function there. And remember, in hydrogen atom, the solutions also decay exponentially at large distances. So one can interpret that as tunneling, if you like. But we're using more classical language here. Does that make sense?
Yeah, thank you.
Yeah, thank you. No, great questions. I might have to speed up a little bit. Now talking about data analysis, why do we have to do a new search, right? I mean, people have done searches for binary black holes and binary neutron stars in the past. Why do we have to do a brand new search for systems with large left numbers? Just to take a step back a little bit, there are many examples of proposals of what other more exotic types of compact objects could be out there in our universe. I just want to mention this slide just to say that, in the early inspired regime of the dynamics, things are relatively well understood because there's a post-Newtonian dynamics, and one can capture any sort of new physics through some coefficients that we understand and we can interpret physically. But the problem is that when these objects, say you have a binary boson star, let's say, the merger regime is very different from those of black holes, of a black hole merger or neutron star merger. In those cases, one would, in principle, have to do a bunch of numerical relativity simulations in order to obtain such waveforms, which is necessary to do a search in the public, in the LIGO-Virgo data. The problem, though, is that numerical relativity simulations are extremely expensive to do. So here is a plot extracted in the 2013 paper by the XX collaboration, which has conducted a series of binary black hole coalescence simulations with different mass and different spin configurations also. And my understanding is that up until recently, let's say since the program started and 10 years moving on, up until recently, there have been only about a few thousand binary black hole numerical relativity simulations, because depending on the number of orbital cycles these simulations take, it can take up to even a few months to complete just one waveform simulation. So these are incredibly expensive solutions. And so let alone if you want to do it for, and this is even just for vanilla binary black holes, right? And let alone trying to do it for like exotic things, binary boson stars and all that. I'm aware of a few examples of numerical relativity simulations in those cases, but as far as I'm aware, you cannot do a search with just a few waveform models, right? And so the nice thing though is that at least in the inspire stage of the binary, as I alluded to earlier, one can capture many of the physics through parameterizations that we understand well. And in this case, we actually understand exactly how the Luft numbers appear in the inspire regime of the binary. And so the strategy moving forward, that I would advocate for doing any type of new physics search is to just ignore the merger. So the price you pay is that you have fewer SNR in the detection, but it's an SNR that you don't know how to model anyways, because you do not know what the merger signals would actually look like if these things exist in the data, right? So the strategy moving forward, which just to focus on the early inspire regime where things are understood, deform the inspire waveform from those of vanilla binary black holes, and then do a search based on those new parameterizations. And what's nice is that with this approach, even though I've been focusing only on gravitational atoms as my favorite BSM example, this strategy in principle would apply to all types of new compact objects, as long as they're covered by our new parameterizations. For example, we know that how the Luft numbers appear at the 5th post-Newtonian order in the phases of waveforms in this overall lambda tilde parameter, which is a mass-weighted combination of the individual lambdas of the binary system. This is a slide to emphasize why do we need to do a new search. I mean, you can ask, like, in the past, people have done binary black hole searches. I mean, would the dephasings be such that one would still capture these signals using binary black hole templates, but maybe the trigger parameters are very different, are absolutely biased, right? So this is a plot that shows that would not be the case, where there's a quantity that's often quoted in the data analysis literature that's called the effectiveness E. And what it is that it is basically an inner product between a waveform of a binary black. Unfortunately, I don't have my cursor. It is the inner product between a binary black hole. So what happens is the following. You have a template bank of binary black holes. So you grid the parameters in masses and spins, and you have a bank of binary black hole templates. And suppose you inject a waveform with large Luft numbers, and you can ask, does any of these templates in this bank will be able to recover the SNR, the full SNR of this new signal? And that is basically what the effectiveness is. The long story short is that in this plot, we show that a typical binary black hole template would miss a vast majority of the parameter space if you have signals with large love numbers. So in the region with red, you see the effectiveness drops to about 0.75, and that is unacceptable in the data analysis literature, because the gold standard in the literature is to have an average effectiveness that's above 0.95 or 0.97 or so. So the upshot here is that, if there were new signals in the data, one would miss them with previous searches that use solely on black hole templates. Here is just to impress upon you that, again, we understand how the love numbers appear exactly in the phase of the waveform in Fourier domain, where in bottom left, you see that lambda tilde appears at v to the 10, so the so-called fifth post-Newtonian order in the waveform. In the interest of time, I will skip through some of these details. Just to say that we did a search on all of the public LIGO 01, 02, 03A, and 03B data, and we did not see any new signatures. Our most significant trigger is consistent with noise, as it is only about 2 sigma away from a noise background distribution. What is nice though is that, as I discussed, as I mentioned earlier, is that we were using this in-spiral only strategy. We were able to recover many of the known binary black holes that were previously identified with a full in-spiral merger ring down waveform. Of course, the price that we pay is that we have fewer SNR, but that kind of is the whole point if you want to do a brand new search. At least we know that the waveforms work, the pipeline works. It's just that there's no new physics that's loud enough, at least, for us to detect in the data. Won't go into details here in the interest of time, except just to say that one can, given the absence of detection, one can place constraints on the merger rates of new types of compact objects. And here are a few plots showing what do these constraints apply to several model parameter space, whether that's what we call mini boson stars or the superradiant clouds that I discussed earlier, or something that's known as massive boson stars with their self-interactions in the scalar sector. The final slide here is just to motivate that this in-spiral only strategy, I think, is promising. If you care about anything else that is not quasi-circular binary black holes, for example, certainly one interesting astrophysics effect is if you have not just circular orbits, but you have eccentric orbits, highly eccentric orbits. In those cases, as far as I understand, there are very, very few numerical relativity simulations for those systems. And so there definitely is not enough waveforms to detect them, even if you want to in the data. And so again, I would advocate just focusing on the in-spiral regime where we understand, at least to some degree of accuracy, how eccentricity affect the in-spiral regime of waveforms analytically. And so we can try to detect, or at least search for, highly eccentric orbits with this in-spiral only strategy. That's it. I think I am spot on time. So thank you for your attention.
Thank you, Horng Sheng,
Thank
for a
you.
very interesting talk. Any questions? I can start actually. So, so first question. So what is your? I mean, okay. So the love numbers of black holes are 0, but what is the? Why is it 0? I mean, usually when we have such a simple result, we have an explanation. So I know that that was discussed in the from a symmetry perspective recently, right? So is that what you? Is that your view that this is kind of the underlying reason for?
There certainly are papers in the literature already that try to relate the vanishing static left numbers to some underlying symmetry. I think it's interesting though that there are various papers on this topic and they all kind of disagree on what exactly are the symmetry structure. And so the reason for that is that it's a little bit tricky. It's tricky in the sense that I think at the center of all of those debates is what exactly is a right near zone approximation to the Tucholsky equation that one should work with. So it turns out that, remember I discussed, and I mean, Shara, you would know for sure that, that these near region, far region approximations of the radial Tukosky equation. And it turns out that if you truncate, by near zone, we just mean that we fully capture the event horizon, the boundary condition of the event horizon, and we neglect infinity, right? The poles at infinity. But it turns out how exactly you truncate, which terms you truncate in the radial equation, gives you slightly different, killing vector, underlying symmetry structures. So I think everyone would probably agree that these are at best some sort of approximate symmetry, because this vanishing, all of this discussion of symmetry only relies on the near zone of the black hole, but not the full radial equation. So I think everyone would sort of agree that these are only some kind of approximate symmetry at best. But the exact symmetry that it captures, I think, is still very much in debate in the literature. Yeah, I think for Schwarzschild it's easy to understand, at least for Schwarzschild, in the static limit, this is full equation that one can work with. But for Kerr, it seemed to be a little bit trickier.
Yes. Thank you. More questions, please.
If I understand correctly, we can measure the alpha, the gravitational fine structure constant, using gravitational waves, and we can do the same thing for the love numbers. So why would someone want to measure the gravitational fine structure constant and not the love number? Does it have more benefits than measuring the love numbers, besides telling us the shape of the hydrogen-like formation?
So if I understand you correctly, so at least in this particular example, in the gravitational atom, there's a one-to-one relationship between alpha and the Love number. But the Love number is a universal parameterization that applies to not just the gravitational atom, it applies to neutron stars, it applies to white dwarfs, it applies to the Earth, except we don't see emergence of Earth, but it applies to any astrophysical body, right? And so at least, by measuring, I think the zeroth order at least is to be able to find a signal with large Love number, however large that lambda is. But if such a signal exists, then I'm sure there will be a lot of debates about whether on the underlying nature of the source of the system, right? And then, okay, if one speculates that it is a gravitational atom, then one can say what alpha that corresponds to. But the search for Love numbers is really sort of model agnostic. It tries to parameterize, any new physics in lambda, and that would catch a wide net of possible signatures.
Thank you.
Yeah, you're welcome.
I have a question. Hi, Horng. This is Barak Kol. Thank you for the talk. I wasn't able to follow it in full. I intend to watch the recording later, and thank you for the very interesting work. I think it's obviously an important result. I want to ask about the imaginary part of of Kerr's love numbers. I don't know whether you spoke about them here. I know that the real part, if I understand correctly, vanishes, but the imaginary part does not. And I've heard some interpretations of it as describing some kind of dissipation. And I was wondering whether you want to comment on that, whether you have any insight into the fact that they are non-zero and what do they stand for?
Oh, they are absolutely dissipation. I think no doubt about it. I think so. There's a part of my talk where
what kind of dissipation?
What kind of dissipation? What do you mean by what kind of dissipation? It's the transfer. It's an effect.
There are many dissipative processes in the universe. If two bodies are moving against each other, then there is friction and there is dissipation. In other physical systems, there are other mechanisms and there are other forms of dissipation. So how should I be thinking about this one?
Oh, it's just the fact that the event horizon is this one-way membrane, right? The event horizon of a black hole is this absorptive membrane, if you like, where anything that falls into it does not escape. That is a source of that makes the whole system an open system, right? It's not a closed system. It's a dissipative system. Now, So if you watch the video, I did actually try to motivate and explain how the imaginary term.
I really missed most of the talk.
Yeah, no worries. Yeah, no worries. You can shoot me an email whenever you want to. But in my talk, I did describe how you can infer, or you can distinguish the conservative versus the dissipative terms by reading off the real and imaginary parts of the total response function. And so the easiest way, I suppose, to see in the Kerr context that this is dissipation is that in this slide that I'm showing here, you see that the imaginary terms has the superradiance term in it, right? Which is well understood in the literature to correspond to sort of spontaneous extraction of energy, or spontaneous, or losing energy to a Kerr black hole, depending on the black hole spin.
Superradiance is concerned with non-zero frequencies, right?
Yes.
And
so
and the imaginary numbers that we are discussing, isn't it static background?
So the superradiance
responds to a static background.
So you can have superradiance still with zero frequencies, right? I mean, I don't know if you can see my slide right now, but
I can see it
okay.
Somewhat.
So when omega is zero, when little omega is zero, which is the frequency of the external perturbation, right? The imaginary terms are still non-vanishing because there's black hole spin, because there's a new time scale. In order to have dissipation, you need to have some kind of time varying background, right? Some kind of time variation. And so in the case for a Kerr black hole, even in the static limit, when omega is zero, because there's a spin of the black hole acting as an additional time scale, there is dissipation. The intuition here is, my intuition at least, is that when you have a rotating body, but with a static perturbation, if you go to the co-rotating frame of the rotating body, you perceive in this co-rotating frame that the static perturbation actually varies with a time scale that's proportional to the spin of the black hole. So there is some effectively, all it matters, I guess, to sum it up, in short, in order to have dissipation, you need to have a relative time dependence between the motion of a body and the external tidal field. Okay, does that make sense?
So, well, remind me, when we, in the usual sense that we discuss superradiance as waves impinging on a black hole, does it apply also to the zero frequency?
Yeah, that applies. Yeah, because it applies. If you look at the superradiance term again, I don't know if you can see my slide, but the superradiance term where omega is zero, you can still have non-vanishing dissipation.
Yes, I can see the slide, but I wasn't sure about the I wasn't sure about the interpretation, whether this is about the love number or about superradiance or about superradiance.
It's both. I mean, so in the total function, the total response here, the real term, the real part of the response is the love number, and the imaginary terms are the dissipation. But you can absolutely have dissipation in static limit when you have spins, when you have some other new time scale, for sure. You don't have dissipation when they synchronize, when m omega equals to little omega. That is when, when there's no dissipation. In astrophysics, we call this tidal locking. In astrophysics, we call this tidal locking. So the fact that, in the Earth and Moon, Moon is locked to us, and the fact that we see the same side of Moon, that is because omega of Moon synchronizes with its own spin.
Yes, I just taught this phenomena in my thinking physics course yesterday, actually.
Okay. So yes. So when when the spin of the black hole synchronizes with the frequency at which it orbits around us, then there's no dissipation. But that's only in that limit.
Okay. So thank you.
No, thanks for coming.
Okay, great. Any more questions? All right. If not, let's thank Horng Sheng again.
Thank you. Thank you for having me.
Thank you for a very interesting talk, and I'll close the recording.